Here it is on my GitHub at Polymath/Nomad. And first of all, you should make sure that you move over to the AppLab branch. So here is all of the files, and so you can get this onto your local machine with the git clone. Of the repo, and this is Nomad. I'm not going to do it because I already have everything on mine, so I'll just go into the Nomad directory here and show you what we got. So here's the readme file, goes through. This is kind of an old place where I used to keep track of everything I was working on, so it's not too up to date. Then you have the folders ELP, where all the three-dimensional files that show the locations of the holes on each of these different types of helmets. And so here's the example from our lab, just so you can see what it looks like. This is each row and column, individual location, and a three-dimensional coordinate of where it is along with its name. And this was then done with a tool called a Polymath Digitizer on someone wearing a helmet at the time. And so it could probably be improved, and as you can see, it's a little bit shaky, the digitization of the location. Some of these other helmets were done on multiple people and then averaged together to get a better representation. So that's one of the files that's used. In documents, you have some things like this diagram of how the program works. Which is important if you get confused along the way or troubleshooting. And we'll go through some of that in person right now. Examples gives a couple in progress files that are saved as you're working on a montage. And these can be used to load into Nomad to test out certain features. You can also save your in progress montages as mat files that then you can load in and keep working on. And finally, this utils folder has all the functions that we're going to use. So for instance, the GUI folder has 4 different M files here, which each have an attaching fig file, and these are the way that Matlab organizes the 4 GUI screens that you come across as you run through the program. So the order would be settings, schematic, assign mux, and then output, as we'll see. And you can also see in the, well, let's look at it. You can see in the Nomad workflow diagram, which is shown right here in docs. Okay, so here you can see the main function Nomad opens the settings GUI. You run through the settings, then you go into the schematic GUI and you indicate which locations you want to put your sources and detectors. Then you go to this assign mux GUI and you allow the program to identify which numbers of lasers and detectors it's going to put in each one of those locations that you specified in 2. And finally, once you're done doing that, then you, that's actually a typo right here. This should say output.gui. And this is going to save a number of files that we're going to need, including the GDF graph definition files, it also can save a diagram of where each location is on the head and what source and detector are going to go there. And it can also save something called a montage file that's used by the pre-processing and analysis programs in the normal workflow, which we may or may not end up using. Okay, so you can get this software onto your computer however you want, and then once you have it going, oh, I just wanted to also mention in here, these other 3 folders are functions related to each of those different steps. So the schematic step here that makes the diagram, the output, which has functions that make all the files I just told you are outputted, and in assign here are the functions including these new ones I was working on for multiple modulation frequencies, the functions that assign the different mux numbers or the different order of lasers to come on. We'll go through that in a little more detail as we go here. Okay, so I'm going to close this and we'll move over completely into Matlab. And so to run the program is easy. Just type in Nomad. You can also run it from the terminal if you'd like. At the same time, I'll show you over here. Actually, no, I won't show you the necessarily. Yeah, why not? So subl nomad.m. So this just opens up a text editor and shows you what the code for that nomad.m file is, and you can see it just adds a bunch of paths, sets some global variables, and opens up the settings GUI. So we can even go to that next, just to get ready. So we open up the M file, and this is where things get pretty complicated. There's a bunch of these functions with a bunch of comments that are auto-generated by Matlab, and each different function is associated with either like an entry where you enter data or a button that you might press that does things. And I'll show you a couple examples of this. This might help you troubleshoot if you get stuck somewhere. For instance, this function says what happens when you press the OK button, which essentially will write all of these settings into memory and eventually move on to the next GUI, the schematic. Okay, but now I'll mostly focus on the software itself. So I'll close this and I'll show you how we can set up a simple montage with a couple sources and a couple detectors. This won't be using the multiple modulation frequencies for now, this setting down here. I'll just show you the basic where you have to keep each source that comes on separate from the other sources that came on at the same time. So we're going to use the green helmet. You can also load in your own by pressing custom, which we might end up doing, but I've loaded the green helmet right into here. These settings here indicate the maximum distance at which we expect to get light from a source to a detector, which is about 60 millimeters, 6 centimeters, and then the min distance. We don't want sources too close or they'll oversaturate the detector and the light won't go down into the brain, so that's about 15 millimeters. We don't want just one montage per subject. This software can loop through and make multiple montages all in the same file. We want only one wavelength for now, but this is where we could set it to 2 to indicate that we want 690s and 830s in the same locations on the head. Let's say we want for now just 4 detectors and that we're going to use 16 sources, 2 banks of 8. And we'll say we set the system to mux 8 so that 8 lights come on, 1 at a time, 1, 2, 3, 4, 5, 6, 7, 8, and then they start back at the first one. That means that at any given time 2 lights are going to be on at once. And then I press go. So one other setting that I didn't indicate there was the automate sources, and I'll show you what that would have done in a second here. So what happens next is, based off the 3D locations of each of the sources and detectors, the software then flattens that representation in 2 ways. One is by a scatter plot on the right here, and the other on the left is a more simple geometric representation of the rows on the head. And this allows you to pick, based off maybe something that you've already designed, or the location that you can see roughly where it is on the head, where you're going to put your sources and where you're going to put your detectors. First, you put the detectors, and the gray areas here indicate locations where detectors are possible. You can actually change if each row is considered a source or a detector by editing the ELP file. At the very top, these S's and D's indicate whether each row is going to be considered a source or a detector row. So, in your software, you're going to select 4 locations. In this case, I'm going to select locations that are relatively spread out. My software is pretty slow when it does this on my computer. I'm not sure what it's like on PCs in the lab. And then I'll pick one more detector location. Okay, now I'm going to put in 16 sources. So you can see as each of those detectors goes in, the source locations begin to be colored red, and they're colored red with increasing saturation depending on the distance between the source and the detector. So in essence, they're indicating how much light would get to I add the signals together. So you can see these dark red areas indicate that that's probably a good place to put a source because it's within a range of multiple detectors and nearby. And when you click that Automate Sources button, it automatically selects the first 16 most saturated squares, or the squares that in my logic had the best chance of having a good signal. So now I'm just going through here, and of course you might want to be more systematic when you do this, but I'm having trouble because it's very slow right now on my computer. You might want to go through more carefully and select just a particular row where you want to put your sources and detectors. But here I go, just selecting the 16 locations. So this would be an example of a more spread out montage. Slowest seem things to be drawing these lines. I tried to fix this lag. So that's a good challenge if you're up to it. Okay, just have to put 2 more. So I'm trying to spread these out because remember that there's going to be 2 on at any given time. And so we want to make sure that those 2 have enough degrees of freedom on the head that there's room for them both to be on. Okay, so there's the last one, montage and helm, and maybe in later lessons we'll see that this is where all the information about what's going on behind this, everything there is to know about the helmet, agnostic to all the individual montages that might be made with that helmet. The montage indicates the individual locations in this particular instantiation of the helmet of where you want the sources and detectors to go. And we can look at the variables that are inside those, of course, by clicking on them. Maybe. Maybe not. Okay, so I haven't read this in a while, but you can read this. It probably says what I just said. At any given time, you can actually go back, or you can restart the program as well. I mean, you can restart that particular onto the next one. Generally, going back sometimes messes things up, so you better off to just start again if you're going back to the first step. So here's inside the montage structure, and you can see things that are unique to this montage, like the number of detectors and the number of sources, but also now the locations of all the detectors and the locations of all the sources. These are the variables that were used during the functions in the schematic making. So here there's 16 sources, that's their XYZ coordinates. Here's 16 sources, that's their XY coordinates. Rows and columns is what RC stands for, so it's the rows and columns of this matrix. And helmet location is the original helmet. So I can tell you more about these if we get stuck. So on to the next step. So when we're done here, we press done. One other thing I didn't mention on that screen was over to the left there is some buttons that say source the detectors out, or source the source for our montage. Oh, one thing I didn't mention that you need to do, of course, on your system is make sure the AppLab branch. So it's going to be very important that we use the AppLab branch, because the branch is stale now. We are in the third step, which is the step that assigns to plot bananas. So this creates a 3D shape of the head based off the location of each source and detector, and that takes the convex hull of all those points to make this shape, and then it draws a red line that has increasing darkness depending on how close the source is to the detector, the lines between the source and the detector. So you can move those around and kind of roughly see where you get more or less coverage. There's probably a better way to implement this in the future. As you'll see, click on channel stats as well, and this will show you the distance from 15 to 60 millimeters and a count. So there's 1 or 3 channels at that distance. So you want a pretty good range of distances with a peak around usually 30 to 40 millimeters. This one's not that good. Okay, so then you want to select an individual montage and say show. It will have squares that indicate where to put the detectors, as well as the letter detector that you need to put there. And then it has these locations where the sources are going to go. And our job on this GUI is to assign these, and then the numbers 1 through 8 to another 8, such that there's no 2 on at any given time with starting. The color button is going to go through, in this case 10 times, and start to put range of that detector here. You can even, if you're getting advanced, you can parallelize this so that random tries is correct. But let's see what it did here. So what it did is another 3 nearby, because that's within the range of this detector. There's a 3 over here. So it's separated out the 1s and 2s and 3s and 4s from each other, such that now there is different numbers. Then in order to pick which bank of sources it uses, it starts on the left and goes up and down and assigns the first one it finds left of all the greens. This makes it easier. We can change some things here like the coloring style, which we don't need. We can parallelize or use a different algorithm to try to assign the sources, which we don't need. We have a given detector. So this is showing the 8 different mux numbers and the 2 different banks and each detector, and it's making sure that there's not 2 dark squares within one of these columns, because that would indicate that for one detector, at both times the 7 is on, that detector is getting light from it. Okay, so that's one thing it outputs, and then it outputs this diagram of each source and each other source and whether it's in the range or not, and tells you at the top if it's good or bad. Generally, the code is made to make sure that it only outputs good montages, and this came from one bug. You could press this again and get numbers move around. When you're done, you press done. Okay, now finally it's going to open up the output. Here's the output where you can change some settings here, but in general you just want to replace then the folder I'm running the files from. So I'll call this schematic. Let's actually open up the file that it saves once it does that. Huh. Didn't seem like it actually saved. Maybe I closed it too fast. Let's try that again. Okay, so I pressed the button again and go to the desktop and go test. And let's leave this open as it does it, and I'll show you what's going on here. So here's all the rows and columns. Everything's white to keep your focus. Here's the column labels as well. This title needs to be moved to fix it. If this save function isn't working, then perhaps we can just take a screenshot of this when we fix it, but you can see that this tells you for the red and the green bank, the 2 different banks on the machine, where to put each source and where to put each detector. Not only does it tell you the number of the source and the letter of the detector, it also tells you which exact row of that column off to the top right. So that's the 4th row, this is the 13th row, the 10th hole, and the 3rd hole when you count from the front. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So with this, you can set up the experiment just how you need it. Okay, oh, and it did save the file. So here's the BMP file on my desktop, and here's what it would look like that you could print off and save in your experiment folder. Okay, and then the next output is the montage file that's used by the analysis software. So I'll also save that on the desktop, and I'll save it as test.montage, and I will open it up to show you that what it does, probably good to open it up beside the schematic, is it tells you the channels. So now we know we have 32 channels, 16 sources and 8 sources of light times 4 detectors. Each detector gets 8 different signals before moving back to the first signal. And even though there's 16 sources, each detector only knows about 8 of them. So the combination of 4 detectors and 8 sources is 32 channels. You can see that each detector has a set of rows here. RC4 is the right C4 A detector right here. And then you can see that this montage file is indicating the closest source with that number 1 through 8. So 1 is RD10, which means that RD10 right here, this one, is closer to A than this one. And it does the same for 1, 2, 3, 4, 5, 6, 7, 8, and then the next detector, next detector, next detector. Here's the wavelength and the modulation frequency, and we'll likely need to change this file once we use multiple modulation frequencies. Finally, the last output is the graph definition file, which is actually going to save a folder. And we're going to save it in the desktop, and we'll call it test. Oh, that didn't work. Oh, no, it did. Okay, so on the desktop, it creates a folder named with your helmet name. That's probably not the best name. We might want to change that one day. And then it saves a series of folders which can also grow if there's multiple machines, if there's multiple montages for a participant. Oh yeah, it looks like it didn't save all the files, so let me try to actually do that again. Let's try test 2. Looks like it doesn't name it right either. Okay, so let me try pressing this button. Oh, it didn't put one there. Okay, so I want to save it on the desktop, and I want to call it test, but that won't really work probably. Okay, let's see, what did it do? It should make 3 folders inside here, AC, DC, and phase. So let me go to the Nomad folder where it looks like it saved another one here at one point. Oh, same problem. Okay. Looks like it's looking for this file in the wrong place. So let me try to fix that with you here. So I'll make a directory called output, and then I'll go into utils, and I'll go into output, and I'll copy GDF template 2 . Folder, and I'll try that again. Done. Okay, so it worked. And it also saves this funny thing, which I don't use either, which was something Kathy wanted. This is going to save it as a BMP, which I can cancel. This shows you for each mux number and each detector how tall the bar graph should be that you're looking at in the GDF file. So this is showing the distance between that source that's the closest to that detector and the detector. So the closer they are, the more red it is. There should be more light getting there, for instance. And this is the same values that are saved in the GDF folders. So let's look at those. Here's Kyle Mathewson, Nomad, and I saved it right here, which I'll delete in a second. I think one of these is empty because there's only one machine in our lab. And then here's AC, DC, and phase. They're all very similar. there's a GDF file, and then one for each detector. Detector A through D. 1, 2, 3, and 4. So let's open up each of these, and we can see that each one represents a detector. There's detector A. This is the standard deviation of the phase, and this tells the graph. This tells Boxy what color to color the graph and what size to make the graph so that they'll all be the same. And this will match up if we look at the rows of A here. These color indexes would match up with them. So 16, 16, 16, 7, 16, 16, 1, 1. And there'd be a file like this for each of the detectors. And we want to use so there's detector D. Looks like it should be 7114 7716. These numbers 714 just represent some color in Boxy software, and they're just saying for that mux number how big to make, how colorful to make the bar graph, so you can quickly identify channels that are really close as red or blue and make sure that they are getting a good signal. That last picture that I just closed looks better when you're using multiple machines, because there's multiple top and bottom sections to it for the two different machines. Okay, finally, and we can go and look in these files. You can see that as we've been working, a lot of extra stuff has been added here into the montage structure, representing all sorts of things like where the GDF files were saved and the path, the schematic, and a big matrix that represents all the sources and all the other sources that it uses to assign the mux numbers. And we can talk more about that in the future. Finally, you can save this workspace if you want to go back and load it in the first stage and work from here again. Maybe move a source or a detector around, for instance. And then you can press exit and close, and you're done. And all the files that you've made are now saved wherever you saved them along the way. So that's how we use Nomad in the traditional sense. Now I'll make another video and we can work together with how to do these things once we have to use multiple modulation frequencies at the same time.